Hello, myself Subham Aditya, enrollment number BT23 CME 083. Today I am here to present my transport phenomena assignment, which is based on the topic thermal conductivity of liquid and gases. So, shall we start? So as you can see, thermal conductivity of pure gas from kinetic theory is given in the expression K is proportional to 1 by 3 CV delta lambda V bar. CV is known as the heat capacity per molecule, and lambda is the mean free path, and V bar is the average molecular speed. So here lambda is directly proportional to the 1 by n into epsilon. So this is the given derivation for the K effective calculation. As we can see, the K effective for a mixture is given as summation alpha is equal to 1 to n x alpha k alpha upon x beta phi x beta, where K mixture is the thermal conductivity of the mixture. Is like two components of mixture, and x alpha is the mole fraction of the component of alpha. Like we have a chlorine or air, so chlorine can be the alpha component and air can be the beta component. So K alpha is also the thermal conductivity of the alpha component, like chlorine and air. So chlorine thermal conductivity is K, and for phi alpha beta is the interaction parameter between species alpha and beta. So for gases, transport properties like viscosity and thermal conductivity depend on molecular motion and collision between species. So it is saying that transport properties like viscosity and thermal conductivity, these two depend upon the molecular motion and collision between the species. So help with these two sentences we can derive the thermal conductivity, like K is inversely proportional to the collision resistance, and using Wilkie's method you know that the viscosity of mixture is summation of x alpha, viscosity of alpha upon summation of beta x beta phi alpha beta. So like this is for the viscosity of the mixture. And now for the thermal conductivity of mixture, we have studied above, like summation x alpha k alpha upon summation x beta phi alpha beta, and physical meaning of denominator is given here. Represents effective resistance to heat transport of species alpha due to beta. Collision with itself means alpha, collision with other species means beta. So expressions for interaction parameter phi alpha beta. So phi alpha beta is given as 1 upon under root 8 in bracket 1 plus m alpha upon m beta. For reference, m alpha and m beta are the molecular weight of the given species, like alpha beta, and in the power minus 1 by 2 in bracket 1 plus k alpha upon k beta is the thermal conductivities of alpha and beta की power 1 by 2 into molecular weight of beta upon alpha की power 1 by 4 का whole की power 2. So this is the phi alpha beta, right? So now we can move above and let's solve a question here. So we have took a question from the book BSL, Birds and Stewart. The question says that thermal conductivity of chlorine air mixture, predict thermal conductivities of chlorine gas mixture at 297 K Kelvin and 1 atm for the following mole fractions of chlorine and air. So both chlorine and air viscosities, thermal conductivities and heat coefficient is given. So yeah, so these data should be assumed in solving the question. So from this data we can calculate the phi alpha beta for both the cases, right? So yeah, numbering chlorine air corresponds 1 and 2 respectively, inserting their given property. So we can calculate these two values, and for binary mixture we have to calculate the thermal conductivity of the mixture. So like we know the formula, right? X alpha K alpha upon X alpha plus K phi alpha beta plus X2 upon phi beta. So using this expression K mixture, we can calculate the thermal conductivity of mixture at different x's, right? Like at 0.5 the thermal conductivity of mixture is 0.0506 Kelvin per centimeter per second square Kelvin. At 0.5 0.0675 is coming. At 0.75 the thermal conductivity of mixture is 0.0800 Kelvin per centimeter second Kelvin. So yeah, we calculated the question. Moving forward, the next question. The next question, it is also from the book Bard and Stewart. Thermal conductivity of a quartz sand. So now we have to calculate the thermal conductivity for a quartz sand. So sample of quartz sand at 20 degrees Celsius is given. Like here we can see that. The volume fraction is also given. K cal per centimeter Kelvin is also given, and water air volume fraction is also given. So we have to estimate the effective thermal conductivity of sand. In first case when it is water saturated, and in second when it is completely dry. So using this expression K effective upon K naught, we have to calculate this. It is given in the question, and here n is the number of solid phase compared to the prediction of sphere, like G1 G2 G3 is equal to 1 by 3, right? And in B part use the K1, which is volume average thermal conductivity of the two solids, observed values accurate with about 3%. Yeah, so it is the G1 G2 is equal to 0.144 and G3 is 0.712. So we have to use this G1 G2 in upcoming solution. Yeah, so here for species G1 G2 G3 is equal to 1 by 3, A1 is equal to 3 by 2 plus Kj upon K naught. The resulting A1 values from equation water sand A naught. At A naught we have is equal to 1, sorry, alpha naught is equal to 1. At alpha 1 it is 0.183, at alpha 2 it is 0.439. With the help of above expression, values of alpha came. Now we have to calculate the K effective, right? So putting the values of alpha naught, alpha 1, alpha 2, yeah, in this formula, K effective upon K naught is equal to summation alpha 1 phi naught K1 by K naught upon summation alpha 1 phi 1. So using that expression we have calculated the K effective, which is coming out to be 6.3 into 10 power minus 3 calcium per centimeter second Kelvin, right? Yeah, so now we have to calculate for the completely dry basis. So for completely dry, the alpha naught is equal to 1, alpha 1 is equal to 0.00898, alpha 2 is equal to 0.00259. So from these alpha 1s we again have to put it in the above expression, which is K effective upon K naught is equal to summation alpha I phi I into Ki upon K naught upon summation alpha I phi naught. So again we have put that in the equation. From here the K effective is 0.38 into 10 power minus 3. So as we can see, for the dry, K effective is different than the wet wet sand, right? These two cases, right? For the wet saturated and completely dry. So for these two cases the K effective is coming out to be different, right? Yeah. So again applying the correction factor for dry sand. Yeah, we have to apply the correction factor also in dry sand. Okay. Predicting K effective to observe for the same sand when water saturated at 20 degrees. So when water saturated at 20 degree Celsius, GI values give 3 alpha naught, alpha 1, alpha 2. These three are coming, and with these help of these we have to calculate K effective. Same procedure like above. So from the above formula with this putting alpha naught, alpha 1, alpha 2, the K effective is coming out to be 6.2 into 10 power minus 3 for the same sand when completely dry. So you can see the ratios K1 upon K0 and K2 by K0. So moving upon to the next topic, thermal conductivity of liquids, right? So here you can see the expressions we have to use, like the final expression is K is equal to 2.80 upon Avogadro number into V bar into power 2 by 3 into KVS, and Vs is this Cp by Cv del P by del rho by del P T base T. So using that expression we got a question from the book Botts and Stewart. Let's use this. The density of liquid CCl4 at 20 degrees Celsius and 1 atm is 1.595 gram per centimeter cube, and its isothermal compressibility is given. Okay, so we have to calculate thermal conductivity. Yeah, so as we can see Cp by Cv we have to assume 1. Okay, and the value of Vs we have calculated Cp by Cv, the Vs is Cp by Cv del rho by del P into T. Del rho by del P T is also given, so putting in that we have got Vs, and the molar volume is m by rho. Okay, so we got the molar volume, mass upon density, we got the molar volume. Now we have to calculate the thermal conductivity of the liquid CCl4 which is at 20 degrees Celsius using this expression K is equal to 2.80 N by V 2 power 3 KVS. So we got the K, Vs, N and V. So putting all it in the equation we got 0.110 watt per meter Kelvin. This is the thermal conductivity of the CCl4 at 20 degrees Celsius, right? So moving forward we have came to the end. We got our last question. Okay, this is also based on the thermal conductivity of ethane at 150 degree Fahrenheit and 191 atm from the experimental values. K is 0.159 BTU per hour at 1 atm 150 degree Fahrenheit. So this solution is also easy. Since measured values of K is known, we use method find the calculate rho r tr the condition measured values. Tr we can calculate from here, it is coming to be 1.115 and Pr is coming out to be 0.021. So Kr we got from here is 0.36. Now we know Kc is equal to K by Kr. So putting that in the Kr and K we got Kc which is 0.0442 BTU per hour feet per Fahrenheit. Now we can calculate the K, right? K is equal to Kr into Kc. So we got the Kr, we got the Kc. Putting that in this equation we will get thermal conductivity of the ethane at 150 degree Fahrenheit which is coming out to be 0.0914 BTU per hour feet Fahrenheit. So yeah, thank you guys. This is the my assignment. Thank you sir. This is my assignment. thermal conductivity of liquid and gases. We use the gases chlorine air mixture problem we have taken. Now in the thermal conductivity of liquid we have took the this question like ethane and the other question which was CCl4 using this expression. So we have calculated thermal conductivity in both the cases for liquid and for gases. So now ending it with a thank you.